we'll talk about the why. Because if you can understand factorials and permutations, then I think you're good for the course. Because that's the kind, it's this kind of material that's the toughest to kind of wrap your brain around. Once you get it, though, it's there, and it's there forever, which is good. A group of 3 people must be arranged in a line. All right, so, and we want to know how many possible arrangements there are. If I'm arranging things, then that's telling me that the order is going to matter. The order, I say order matters, but I say order is important. All right. It's a question of, well, who is it important to? Well, it's me because I asked a question. All right. And that's really what it comes down to. But you could think of different circumstances in which the order is not important and certain circumstances in which the order is important. And I think it's kind of a funny little twist of fate, but the term combination is just talking about unique values in no particular order, which is weird because if you're using a combination lock, it very much matters in what order you put the code in. Because if the code is 21731 and you you twist it around to 23117, you're not getting in, right? Because the order of the numbers does matter in that context, but that's actually a permutation, right? So an example of a permutation again would be something like a locker combination, but I'll write combo. Right, whereas a combination is something completely different, and that's something we'll talk about next class because, again, this is the foundation stuff. So I have 3 people, Alex, Brian, and Claudia. They're going to be arranged in a line. There's a couple of ways to handle it. It's a small sample. So I could do a tree diagram. A, B, C is the first person. Any of them could be in that first position, right? It's that driving analogy from before. No, I want to go first. We're lining up. We're going to the cafeteria. For some reason, it seems to matter to kindergartners whether they're first in line. Middle school students don't care anymore. So kindergartners are your permutation. The middle school students would be your combination. Right. So the second person on the line can be anyone who was not in the first position. So if A was in the first spot, then it could be B or C in the second spot. If B was in the first spot, then A or C could be in the second spot. If C was in the first spot, then A or B could be in the second spot. And whoever's left over would be last in line. So C, B, C, A, B, A. Kabakaba. Not running out of things to talk about on this side, so just making up nonsense now. So we have our possible arrangements. First arrangement could follow this pathway, where Alfred is first, Bruce is second, and Catwoman is third. All right. It could go the other way. Maybe Catwoman was first, and Alfred was second, and Bruce was third. Also known as something else. But anyway, these are our possible arrangements. Any branch of the tree would give us a different arrangement. But again, just like I was talking about before, you already see how this is not a method that you can use in all cases, because if the group has 30 people in it, that's a pretty big tree diagram. You don't want to make it. So we need a different approach. So what we do is we take note of how many possibilities there were in the first position, how many were in the second position, and how many were in the third position for each line. What are our possibilities? Any of the 3 people could be in the first spot. Once a person is placed in the first spot, there's 1 less person for the second spot. So there's a total of 2 people that could be in the second spot. Once I have the first 2 people situated, the third person has to be, whoever's left over would be in the third spot. By multiplying these, we get the total number of branches of the tree diagram, which would be 6. All right? But the 3 times 2 times 1 part of it is what's important here, because that could also be represented as 3 factorial, which in your calculator, we'll get to it in a minute, is equal to 6. All right? That's an important realization because, and this has happened in the past, folks have been saying things like, I don't know, it's all spiraling out of control now. They would say, okay, cool, it's a nice symbol, but I didn't need that in order to figure out the answer. And yeah, you're right. If there were 30 people in line, you could do 30 times 29 times 28 times 27 times 26 and so on. If there were no function that was actually built into the calculator, I might even consider doing it that way, you know? But there is a function that's built into the calculator. So what I would do is hit the number 3, and I'd hit math, probability, 4. I'll look in a second. 4. That would give us the 3 factorial. So I put in the first number, the 3. I want 3 factorial. Math, probability, option 4, the exclamation point, and hit enter, and you get the 6. All right. So now if there's 30 people, we would say 30 factorial. Sometimes the numbers get large enough, they get a little out of hand, where you just leave it in factorial form. Like if it was like 100 factorial, I would probably just leave it as 100 factorial rather than writing the real number, because they get pretty big pretty quick. Math probability option 4. And you get that, you see? Look at that. The scientific notation is just terrible. And in this context, and I mentioned this last class, I think, when you have a positive number after the E, if that number is bigger than 9, then just leave it in the symbolic form. All right? So you would have, okay, let me actually just detail that. It's 2.652-ish. You know what? Copy paste. This is where a little bit of number sense comes into play. But, I mean, most people are fine just remembering that if this number here is bigger than 9, then leave it as this. And the reason why is if I were to write this number out, it would be 265252859 followed by 23 zeros. Honestly, I don't even know what this number is called. I'm sure it has a fancy name. But we're beyond like trillions, quadrillions, whatever. That's a huge number. But that's not why we're ditching this notation, because it's equivalent to that. No, that has nothing to do with it. It has to do with the fact that this can't possibly be 30 factorial. Right? To end with that many zeros, we're multiplying 30, 29, 28, 27, 26, 25, all the way down to 1. The chances that we're going to get a number that has this many zeros in it is remote. It's not going to happen. What the calculator does is it only produces the first 9 decimal points, decimal values after the decimal point, and then drops every other decimal value after that. Right? So there were probably a whole lot of non-zero values within this set of 23 zeros, but the calculator just dropped. It just stopped reporting those numbers. The problem with that would be that I'm going to be way off from the correct answer, because if any one of these numbers in this interval here is equal to 1, let's say this number. So hundreds, thousands, millions. If this number, just this one number, was equal to 1, I'd be off by billion. All right, so that's a significant amount of error. I mean, you don't even have to know mathematically what significant means in order to know that that's significant.
You keep saying 23 zeros. Is it 32 zeros?
The first 9 values are there. So this 1, 2, 3, exactly.
Sorry.
All right, so in this case, we would just leave it as 30 factorial. And in all honesty, you've met the standards of the problem by reporting just the 30 factorial. It's telling me that you know what the situation is really talking about. Whether or not you can type something into the calculator, I mean, sometimes there's value to that, but not always. All right? And besides, this is the launch pad for what we're going to do. So this is the basics. That general rule, n factorial is equal to n minus 1 factorial. That's a mathematical way of representing this. It's really kind of interesting because, one, I don't know, I mean, I didn't come up with this. This is like the textbook definition, but this is probably not the way I would think of it if I could define it in general terms. So this is a really great way if you actually wanted to look at a graph of all possibilities when you're dealing with factorials. What this is saying is if you have something like, for example, 5 factorial, that would be the same as 5 times 5 minus 1 factorial, which is the same as 5 times 4 factorial. Well, yeah, 4 factorial is 4 times 3 times 2 times 1, and I'm multiplying that by 5, so that's the same thing. The question would be, well, how is that useful? And it's a good question that we're going to address on the next page, but that unfortunately means next class. All right? But there is a good reason for doing something this way. A line consisting of 2 people must be arranged from a group of 3 people. So that's telling me that instead of lining up 3 people, I have 3 people available. I'm only going to line up 2 of them. I'm going to tell the third person to take a walk. All right? So we have A, B, C. All right. So the first person could be A, B, or C. The second person can be any of the 2 people that were not the first person. So B or C. A or C. A or B. All right, so we're looking at 6 outcomes again. And that's kind of interesting because we have a total of 3 here. We have a total of 2 per category there. 3 times 2 is equal to 6. It's like, oh, that's kind of weird. That's the same answer as the previous question. Like, how did that happen? Well, because what's happening here is we're defining the third person as a person that's just going to take a hike. But how, I mean, it's still going to be one person, right? So that third category, instead of being first person online, second person online, it could be first person online, second person online, third person goes home. All right, it's the same situation, in which case C's going home, B's going home, C's going home, A's going home, B's going home, A's going home. All right, but it still amounts to the same situation. I haven't said the word in a while, so whoever is left over does have some value to the situation. So, but I only really care about these folks, right? It's nice to know who's not going to be around, but it's not totally important to the situation. 3 times 8, 30 seconds. How can we simplify this? You see this notation here. It's kind of fun to look at. Subscripts everywhere. It's like, that looks pretty cool and mathy. You know, when somebody's looking over your shoulder at the library, they're going to think you're really smart. But how can we use it? Well, the notation NPR number available number per arrangement. So if you have the total number of people that are available, in this case 3, and you have how many you want in each group, in each category, that would be the notation that the calculator would understand in order to get you the final answer. Right? I mean, it's not the intent, but it's a byproduct where we're really kind of learning this notation so that we know what to type in the calculator. I mean, there's value in knowing the notation just for the sake of knowing the notation, but at this point, it's how can I use the calculator to get me the answer that I'm looking for? All right, so I would type in 3, then I would select the key NPR, and then 2. All right, so that's math. To get to this one, math, probability, I think it's option 2.
Yep.
So 3, math, probability, option 2, and then type in the number 2. It doesn't look like this should actually give us something meaningful, but it does. All right, again, we don't need the calculator for the small samples. We need it for when it gets bigger and bigger. Okay, so that's... So if I had 40 people available, and I wanted to put them in 5-person arrangements, 40p5. Right? What you have, what you want. And that's how you determine an arrangement. And again, there's an implied component here. Because this is telling me, all right, if I want groups of 2 from the 3, I can also start thinking about, well, what do I not want? Right? Because sometimes it's easier to come up with that. The different ways in which you can have failure, because once you have the number of ways that you can fail, then you can work backwards from there. Subtracting, you'll have the number of ways in which you can have a success. Right? So if I were to say, for example, 3p1, in your calculator, that's going to give me a 3. All right? So what that tells me is the number of leftovers, number of ways for a person to be excluded. I mean, it's kind of a bully mentality, but it's like student wakes up in the morning, it's like, all right, I'm in a bullying kind of mood. I think I can take on the whole world. All right. Well, there's 20 people in my class. I only bully in groups of 4. How many ways can I do that? How many different arrangements of people can I get? You know, it's pretty terrible, but you know that's the excluded part. You can think of that. You know, so these are part of the club. These are the people who got cut. You know, you can think of it that way too. Okay. And if you know how many categories there are, there's a lot of things you can do with that. All right, the NPR rule, mathematically, it says n factorial divided by n minus r factorial. All right. In terms of meaning, all we need to know is that we're taking however many items there would be in the full-blown factorial, like in the first example, and then reducing that by some divisor. Right? So it's a subset of the full-blown factorial, because really, visually, it's right here. The whole thing would be a factorial, but I only want that part. If you don't want to go all the way down to 1 when you're doing your calculations, then odds are you're looking at a permutation. Right. And so that's where we're going to leave it today, because the next problem is how we learn about combinations. But I really want you to spend some time thinking about this. There isn't really much to do. It's just thinking for